All right, so may have seen this before, also known as U substitution. It's not entirely true. U substitution is a particular type of substitution. We can do U squared substitution. We can do e to the x substitutions. We got all sorts of different substitutions that we can do. We can do a y equals e over x. Sorry. B equals, it's one of those. I think it's like, it's a homogeneous differential equation. It's towards the end of the packet. We'll get there, but they're all different sorts of substitutions that you can do in order to simplify whatever expression you're working with to make it something that is anti-differentiable. All right? So that's the key. You have something that you can integrate just by looking at it. In this case, I can distribute and then do the reverse power rule, and I'm fine. On a test, that's fair game. We're gonna do it with substitution just so you get a feel for it. But work from the beginning of the course to the end. Don't try to use the most complicated technique to integrate, because odds are you're probably overcomplicating. Right? There are situations where you will need use substitution, and one of the challenges going forward is the idea that some cases require integration by substitution, some integration by parts, some partial fraction decomposite. Like all these names that I'm throwing out there, they're just other techniques. The big question ends up being, when do I use what? Right? So we're going to look for patterns in the expressions that will help us make a determination which technique is the best technique to use. All right. So I got a process written there for you. At some point, I've copy and pasted that from a textbook somewhere. I haven't really looked at it since. Hopefully, it's describing what I'm about to show you. If it's not, then somebody rewrite it, submit it, and I'll give you some bonus. That's assuming it's wrong. All right. So what we're looking for generally is what we call an inner function, a function that's plugged inside another function. But more so, we're trying to get at the idea that if there was some substitution that happened, one function into another, which was the recipient and which one was the one that got substituted into. So it's kind of like chain rule. When you look at chain rule, you identify the inner function and then work around that to take the derivative. Here we're kind of doing the same thing. So we look for things like the base of an exponential, the exponent of an exponential, something that's captured within a sine or a cosine function. You know, things along those lines. So what would normally be a parent function is no longer a parent function. So your parent functions are like y equals x squared, y equals the sine of x, the basic function in any category. So what we're looking for is some function that would be just a parent function if some other funky business didn't happen to it already. So in this case, that would be a parent function if only that one wasn't added to it. All right? Another thing that we keep an eye out for with substitution, especially with polynomials, is whatever we're going to define as our u should be of a higher order than what is not going to be defined as a u. All right? Higher order means higher power. All right? So I wouldn't take a power of 1 to be my u. I want my powers to be 2 or more, something substantial. All right? So what we do is we first identify that u. So I just kind of do it off on the side here. X squared plus 1. I'm going to call that u. The idea is to swap out some complicated aspect of the integral. All right, and a lot of people just go by that. I'll just take the messiest part, and I'm going to call that u. More times than not, that'll actually work. But then what we're going to do is take the derivative of this with respect to x. So du dx would be equal to, if I differentiate this with respect to x, just 2x. All right. Then I solve this for du. There's a bunch of ways to do it. This is the way I settle on. That's the way I like the most. So I multiply both sides by dx. So the du dx equals 2x. That's a differential equation. by multiplying both sides by dx, it's now in differential form. So going right back to the beginning of the course. What I can do now is actively perform a substitution. The first thing I'm going to do, I'm going to forget about the du stuff and just work off of my designation of u. So if I rewrite this and just replace the highlighted expression, I'd have 2x, it would be times that u, because that's what x squared plus 1, that's what I called u, dx. All right? The issue is I can't integrate with two different variables yet. So, Calc 3. I can't integrate with respect to two different variables. So, that 2x has to go. Fortunately, I have a relation that involves a 2x and a dx. Okay? Here's my 2x dx. Here also is 2x dx. So I can change, I can pull out the 2x dx from my integral, leave just the u, and then I can merge these two together and make that my du. Because 2x times dx is what I have defined as being equal to du. So by calling u x squared plus 1, that allowed du eventually to be equivalent to 2x dx. So I have a 2x here, dx there. These two get replaced with just the du. That's what they're equal to. Now I'm working with something that's way simpler than what I started with. Well, maybe not way, because I could have just distributed. But I can easily anti-differentiate this. It would be increase the exponent by 1, divide by the new exponent, plus c. Now this is an indefinite integral. When it's a definite integral, there's a different set of steps that we'd follow from here. But in this case, what I want to do is I want to reverse substitute. I want to replace the u with what it really is. And so we get that as our antiderivative. And you can check by differentiation. So take the derivative of that expression, you should get back where you started. It would involve chain rule, but if you take the power multiplied by the coefficient and reduce the power by 1, you get an x squared plus 1. Then you multiply that by the derivative on the inside. The derivative on the inside would just be a 2x, and there's your coefficient. All right, you show that work if you want. You can do it in the calculator if you want. But at some point, you probably want to check that. All right, so let's just pull over here for a second and talk about checking our answers in the calculator. Because some of these will get so funky in terms of the final answer that you're going to look at it and be like, no way that's right. Especially when we get to integration by parts. I mean, like, there's no possible conceivable way that I did any of that right. And it'll turn out it's perfectly right, but you won't know unless you have a way to check it. Your calculator will be the way to go. So, what I do is in Y4, I hit math. Well, I'm using the derivative function, not antiderivative, but derivative. All right, so math 8, x, y1, so alpha trace y1, and x. All right, so that's math 8 to get that display up, and alpha trace to get the y1. All right, what that allows me to do is put some expression into y1. Y4 is going to take the derivative of that function for all x values, which is the definition of a derivative. Right? The issue, though, is it doesn't do it symbolically, so it won't actually give you the algebraic interpretation, but it will graph it for you, and that's pretty important. Right? So what I would do here is I would take my answer and put that in y1. and I would put the original integrand, the thing that was in the integral, I'd put that in for y2. All right. So we're going to leave this in here. I recommend never clearing that out because it's nice to have it there when you need it. Y2 should be the original integrand, the thing that was given to you, and Y1 should be the answer that you came up with. All right, so what we're looking for is for the derivative of my answer. So I'm actually going to turn that off because I don't need to see what this graph looks like. So hit enter on the equal sign to turn off a graph. No plus c, no. And we don't have to worry about it anyway because it has a derivative that goes to 0. So it'll go away anyway. So by turning off the first function, that takes that out of contention. I don't even want to see that. What I'm telling the calculator to do is take the derivative of what I put in for y1, and that should be the same as what they gave me in the integral. Because the derivative of an antiderivative should bring you right back where you started. Right? So if these two graphs match up, then I'm pretty confident that I didn't screw it up. I mean, you could always make some like really tiny, subtle mistake that gives you a graph that looks so very close to what it ought to be that you think it's right for that. I mean, I can't even think of an instance where that would happen. So zoom 6 to start, unless you have a suspicion that the window would be something else. So I have a red graph, and then over that, it should have, yep, the purple traced right on top of it. All right. For your TI-84s that are not the color screen, let's see if I can do that. Calculator model. I was hoping it held on to my, it didn't hold on to my stuff. All right, well, I guess I'm doing it all over again. Oh, that's where it all went. Oh, they changed the model on me, that's why. All right, anyway, I'm gonna kill this. So original, or your answer, sorry. We'll get to Y4 also, we'll do all that stuff, I'm gonna do it all again. Subtle difference with these calculators though. So, what I should get when I take its derivative, and then we go to Y4. Y4 again is math 8. Put the x in. Alpha trace Y1. Put the x in again. All right. I want my first equation to be off, and the second equation to be on. Also the fourth one. Now, for these calculators, the one that don't have color screens, go to that little slashy thing, so hit the left arrow until you're hovering over that slashy thing, which I think is called the slashy thing, and hit enter once. It changes it from, you know, a regular size line to a thicker line. All right, so what'll happen is, it's actually, I think it's more satisfying this way, even than with the color screens. It'll graph this, and if I'm right, it should trace, so it's basically graphing this in pen, and then graphing over it in Sharpie. Right, so that's what we should be looking at. So zoom 6. Hit the left arrow until you're on it and hit enter once. All right, so it happened. It gave us the regularly drawn line or curve and then boldface on top of it. All right, if you don't like that, go into your table. Now, for wherever this function exists, and it exists in a lot of places because it's polynomial, our y2 and y4 have the exact same values. Right? So that's telling us that they're the same curve. So that's good news. It means I did it right. Now, when you're not using y4, go down, hit enter on the equal sign and turn it off. Because if you have y4 on, but you don't have anything in y1, there's a logic issue. The calculator will spit out an error message. So you don't want that. All right. Number 2, actually numbers 2 and 4, are pretty straightforward in that it's pretty easy to identify what the u should be. It's the most complicated part of the expression. Like something under a radical, for example, other than just an x. All right? The one idea you want to always have in mind is that whatever you call u, the derivative of that should help you cancel out the other part of the expression. All right? Because again, I can't have x's and u's in my integral. I only want u's after I do this. So if there's an x left over after I choose my u and take the derivative and try to cancel, if there's an x left over, I chose the wrong u. All right? So that's a good way to go about it. It takes a little bit of practice, and by a little, I mean a lot. But you'll get there if you're not already there. du dx would be equal to 3x squared. And then the next step is to solve for du. Du is equal to 3x squared dx. All right? I start reproducing my integral. But this time, instead of having radical mess, I'm going to have radical u. And we still have the dx. Okay? So this is what we want to do. At this point, we want to take stock of our inventory. We want to see what we have and what we need. All right? So this is what I need. I need an x squared and a dx. I got that. I don't need that 3. That 3 shouldn't be there. All right? So I'm going to get rid of the 3. I'm going to divide both sides by 3. Because again, all I need is an x squared and a dx. All right? So once I clean this up so that the right-hand side matches what I need from my integral, then I can actually do that substitution. All right? And I can place the 1/3 wherever I want. The du has to be at the end. So I'm going to plop the du there. I'm going to put the 1/3 here, and I'm still going to have the radical u. So now I have an integral that's no longer in terms of x. It only contains u's. Constant multiples are fine. Any kind of constant multiple will be okay. So again, this went here and here. I don't like radicals when I'm integrating. 1/3 u to the 1/2 du. Then I can integrate this. All right, so what is the antiderivative of 1/3 u to the 1/2? What did we say? What was the coefficient? Two-thirds is what we're saying? So we're taking 1/3 and dividing it by 3/2. 1/3 times 2/3 is 3 times 3 is 9. It's the little things in life. When all is said and done, you'll have no problem with the concept of u substitution, partial fraction, multiplicative, improper integrals, forgetting to distribute a negative, and how to divide fractions. That's going to be a big problem. And you know what? In reality, if that ends up being your big problem, you're going to be all right. Because that's kind of why they made calculators. So all right, so final step when you're dealing with indefinite integrals, again, no bounds on the integral, just reverse substitute. Get your u back in terms of x. And then you can do the check. Say it again. Oh, x squared, x cubed? Yeah, you're right. catch. I wish I could blame that one on my poor pitches, but... Alright, so number 4 is along the same lines as number 2. Number 3 is a trig problem, but I feel like got a little groove going here with the algebraic stuff. So we'll do 4 first, then 3. I'll take that as a typo. It honestly wouldn't matter, but I feel like next semester I'm just going to say the same thing. I kind of look at defining my use. So I've given like 10 different strategies already. Find one that you like and go with it. But I kind of look at it as like, all right, if I'm only able to get rid of this part of it, I would totally be able to find the antiderivative. You know, so it's kind of loose in this case, definitely more so in the first 2 cases. But this is the meaty part of it. But it's also possible that I could define u as 1 plus x to the 4th squared. It could be the whole shebang. Right? Sometimes an entire numerator or denominator is your u. And that's what can be so frustrating about it. Because the idea is not like, all right, well, just take the leading coefficient and make that your u. Just take the middle term and make that your u. It's not as cut and dried like that. If somebody asked me, just came up to me like at a tutorial center or something like that and said, all right, I'm trying to learn about u substitution. How do I determine u? Very frustratingly, I would say as an answer, well, it depends. In this situation, you do that. In that situation, you do that. In that situation, you do that. And then 29 other situations later, you'll have a good sense of how to do it. So it comes down to just intuiting what you think the u is and going from there. And then when you do like 100,000 problems like I've done, it's like, oh, this reminded me of the last 30 times I did this the long way. I might as well develop a shortcut to it. So it does come from experience in a lot of cases. Although I will say that if I paid attention more in class, I probably would have got to it quicker. Because I'm sure there's somebody like this here. There always is, where it's like, okay, he's still talking, blah 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 blah. I'll just figure it out later, you know, because I'm smart. All right, now this step is a combination of 2 steps. It's just, we don't always want to have to write that intermediate step. We do want to save ourselves, even if it's like a second. It's a second that you'd like to not have to worry about writing something. So I normally would write to u dx equals whatever the derivative is. But if I'm just going to move the dx over again in the next step, why not just write the dx on at the end all in one shot? I mean, you could show the intermediate thing, du dx equals whatever, and then multiply by the dx. But again, experience. You do this often enough, you're like, it's always going to end up on the other side. Why am I writing this? All right, so have that in mind, at least as you're going forward. If this is your first time seeing u substitution, again, Calc 1 topic that doesn't always make it into Calc 1. If it's your first time seeing u substitution, you're not interested in shortcuts right now. You're interested in like, I want to understand how it works. But if it's not your first rodeo, you have a sense of how it works. Now you're looking for the little tricks of the trade, right? So I called u this guy, and that guy is raised to the 2nd power. I also have an x cubed there. All right, so ignoring the u's now, because I've already done my u substitution. Inventory, this is what I need. We generally are going to have more than we need. So I have those, but I also have the 4. I don't need the 4 in order to match what I have in the integral. So I'm going to divide it out, and it's going to make it 1/4 du equals x cubed dx. All right, so now I have a direct relationship. The x cubed dx is in my differential work on the right hand side. It's also in my integral, so I can do an even swap. So working around the 1 over u squared, I'm going to swap out the x cubed dx for a 1/4 du. I'll clean it up a little bit. 1 over 4. I'm writing u squared on the bottom. I don't like that. I want a power rule. So u to the -2nd du. Now I can integrate. Increase the exponent by 1, u to the -1st. Divide by the new exponent. 1/4 divided by -1 is -1/4 plus c. Can't forget the oh, that's not a 1. See, that's my issue. It's the writing and talking at the same time. That's why I make mistakes. That's why I need a TA. But I can't offer you anything like money or grades or anything, so nobody ever volunteers for some reason. All right, so swap out the u for what it really is. Just don't forget the plus c. Going to lose credit if you forget the plus c. Not a ton of credit, a little bit of credit, but credit. It's credit you don't want to lose. All right. So now to the trig problem, because I find that people who struggle with u substitution don't struggle because of the algebraic stuff. They struggle because of the trig stuff. All right. And depending on how you look at it, it could be not too bad or it could be terrible. One of the issues that people have with trig is that they lose sight of relationships that they know from previous courses. But then another issue that people have is that they're over-focused on things that they learned in previous courses. So it basically says that the biggest problem people have is broken up into 2 categories, and one category is the exact opposite of the other. You either know too much about trig or you don't know enough. Right? Because what a person who's really strong in pre-calc might say is, oh, I can make that 1 minus sine squared, because cosine squared is equal to 1 minus sine squared. That sounds great. Unfortunately, in this case, it's not going to get you anywhere. I mean, it will get you somewhere eventually when we learn how to do that in a week and a half. But tonight it's not going to get you anywhere. The person who actually knows nothing about trig, pre-calc trig, actually would probably go about this with the right kind of mentality, which is really kind of the opposite of what I would normally say, but that's just how it is. First, I'm going to write it as sine of x times the cosine of x squared dx. All right, so subtle difference. I swapped the order. I wanted the thing with the higher power to be at the end. The reason that was the case is because I mean, if I'm just learning about this, well, that's what it was like in number 1 and number 2. So maybe there's something to that. Say it again? Yes. And to make matters more complicated, on the calculator, it's cosine of x, close the parentheses, and square, which isn't either of those, and technically not even remotely mathematically correct. But that's how the calculator understands it. So, yeah, a bunch of different ways of writing it. Regardless of how you write it, this is the way you need to think about it. Because if we got this idea of an inner function, well, I got an inner function. It's cosine being raised to the 2nd power. My inner function would be u equals cosine of x. All right. So the base of some expression being raised to a power, it's always a good idea to start there. If you have an exponential function, we haven't done much with that, but if you have something like e to the sine of x, e to the sine of x is really easy to work with. If you know to designate the sine of x as u, because that's the thing that makes e to the x way more complicated. All right, so by calling the exponent the u, then you're ahead of the game. And we'll explore those as we go. For now, what is the derivative of cosine of x? Negative sine of x. Well, happy to hear that nobody made the common error when it comes to differentiating while in a Calc 2 class. Just can't get it out of your head sometimes that, no, I do actually want to take the derivative here, not the antiderivative. So far too often I'll see, I mean, if you get a question like this wrong on a test, it's because in this test you wrote sine of x instead of negative sine of x. Because you knew you were supposed to go derivative, but for whatever reason you couldn't stop yourself from going antiderivative. Hopefully I didn't just make that a self-fulfilling prophecy. Anyway, sine of x, let me swap out, not there yet, the cosine of x for the u, take inventory, I need a sine x dx. I have a sine x dx, but I also have a little bit more than that I don't want. All right. So what I'm going to do is negate both sides. And that's going to give me negative du equals sine x dx. So now I have something that can be, oh, wrong color, directly substituted. I can now, because sine x dx is the same as negative du, I could pull out the sine of x dx and replace it with a negative du. So I have negative u squared du. Oh, that's way too much space. This looks ridiculous. The internet's going to go crazy. I lost track of my color scheme. Anyway, now I can anti-differentiate this, and we'll get negative 1/3 u cubed plus c. And we know u is cosine. Cosine of x cubed plus c. Now that's the same as negative 1/3 cosine cubed of x plus c. So either notation is fine by me. Just be prepared to have the question given to you in either notation too. Right? So I'll accept it either way, but that means you gotta accept it either way.
Why did you want negative?
Because when we took the derivative of cosine of x, it gave us a negative sine x. So in order to do our substitution, I needed to get rid of sine x dx. So I had to get this solved for sine x dx in order to do that substitution, and it just gave us algebraically a negative du. Page 32.